what's going on? Well, they looked at the isotopics of other elements. Here I have a histogram. A histogram, the bars show you the relative frequency of getting a certain isotope in nature. That's what we are looking at. And these are the isotopes of neodymium. I mentioned before, neodymium, as you see down here, it's got 60 protons. And I can have different numbers of neutrons. And what we see here is the relative abundance of the different isotopes, having the different numbers of neutrons in the nucleus. And this is the distribution, natural. That's the distribution you get for neodymium anywhere else on the planet. So if we dug up the neodymium under this building right now, this is the isotopic distribution that we would expect. We see it everywhere else on the planet. But when they looked at it at Oklo, the neodymium and all of the other elements had similar distributions that were crazy, just whacked. Like, look at this. This is not natural. At least it didn't look natural. Turns out it is. But it looked like it was completely different than anything that we would expect. Now, after looking at it and thinking about it, they realized something. When they started looking at it, they realized, look, if I look at the neodymium distribution from terminal fission products of uranium-235, I showed you those distributions. The isotopes that are created in fission. There's a distribution of them. They started looking at those, and they saw something similar to what I'm going to show you right here. The distribution of the neodymiums looks like this. And what they realize is that they take what you have at Oklo, and you subtract off the natural distribution. So basically, you get rid of this 142 component, pretty much. Once you do that, Oklo minus the natural gave you a statistically indistinguishable distribution to terminal fission products. So this applied to all of the other isotopes. And what this meant, this is crazy, what this meant is that Mother Nature made her own natural nuclear fission reactor, and she buried it, she removed it from the biosphere in such a way that it literally just decayed down into a different kind of dirt by the time we were able to see it again. Now, how does that happen? How does Mother Nature make a natural nuclear reactor? Turns out, it comes down to deep geological time. What ends up happening is that the fissile component, uranium-235, the one that's only 0.7% naturally in the environment, it's got a much shorter half-life than this fertile partner, uranium-238. Uranium-235, the fissile isotope, has a half-life of 700 million years. Now, that might sound crazy to call that a short half-life, but when you compare it to uranium-238, it's got a half-life of 4.5 billion years. That's the age of the Earth. So since the Earth was formed, we've lost only half of the uranium that we started with, but we've lost a lot more of the uranium-235. These things exponentially decay forward in time. But if you go backwards in time, they exponentially increase, which means it increases a lot. So if I go back 2 billion years, the natural enrichment of any uranium found anywhere on Earth would have been about 5%. That's the same enrichment we require for commercial nuclear fuel. And so Mother Nature she'd already had about 3 billion years to start doing, chemical processes through water and through magma and all the different geological processes that occur to concentrate this ore, so that when the water finally trickled down from the water table up above, it went critical, boiled it back out, did it over millions of years, created a lot of energy, a lot of heat. But because it was 2 billion years ago, it just decayed down into a different kind of dirt. Very unique, interesting dirt, but it's just a different kind of dirt, all the same. So what this tells us, this crazy thing, modern geology works. This is considered the quintessential proof that the laws of physics have not changed for at least 2 billion years. This is the smoking gun, that the laws of physics that we know today have been around for at least 2 billion years, because this right here required electromagnetism, the strong nuclear force, and the weak nuclear force. Fine structure constant, alpha, that's part of what this research showed here, is that all of those laws of physics are required to take place to have this happen, and it happened. We can prove it. We can go back and see it now. And so we know 2 billion years ago, the laws of physics were the same as they are now. And so as long as we believe that the laws of physics will continue on for a couple billion years, well, we can just not reinvent the wheel and do it like Mother Nature did. That's an option. That's an option. And that's after recycling, hopefully. We'll see. Well, where do we get radiation from as humans, as citizens of this great country? Where do we get radiation? A lot of different sources. Here's a pie chart from the Environmental Protection Agency. And what you can see is that the average US citizen gets about just under 630 millirem per year. All right, so now we have a number that's not so gobbledygook. 630, that's just what you get for a citizen. About half of that dose comes from medical. I don't believe that there's a competent physician in this country today that would set a bone without an x-ray. Right? You might puncture an artery, you might do some kind of damage. You need to know what's happening inside the body before you start poking around the sharp bone ends. And that just applies for simple x-rays. That doesn't apply to when we have to take CT scans, maybe do some fluoroscopy, some endoscopy, brachytherapy, all kinds of different things that we do with radiation. So about half the dose we get as citizens just comes from medical sources because we like medicine, we like modern medicine. It's one of those nice little conveniences that you get from living in the United States is that you can have access to some of the best medical facilities and practices in the world. But the other half comes from natural sources. The biggest chunk of the natural sources is just the radon and thoron in the air. That's the biggest chunk. You're not walking around with a respirator. You get about 200 millirem a year on average. Actually, we're getting more here on the Colorado Plateau. You get a lot less on the coast, but that's about what the average citizen gets. So this is population weighted, right? You're going to get a lot more out here than that because of the low density of population. But this is a population weighted estimate on what the average US citizen gets. Now, something that's interesting about this are the natural sources. You get some from space, you get some from your food, some from the ground that's coming up. Consumer goods, 2%, there are a number of different consumer goods. But in the industrial category up here, that includes radiography, industrial radiography, oil well loggers, density gauges, all of those kinds of things, but also commercial nuclear energy. And it's less than 0.1%, all of it together. We've got to lump it all together because it's not a lot. And yet that could be the one that scares people the most. Interesting. All right. Oh, I want to ask a question before I do this. If I told you that you did something yesterday that caused you to get 10 to the minus 5 joules per kilogram of ionizing radiation dose. It's a bunch of gobbledygook, but it sounds scary, right? She's got 10 to the minus 5 joules per kilogram. Am I going to die? I don't know. What's that? A bunch of gobbledygook. That is a bunch of gobbledygook. What that is intentional gobbledygook to mask 1 millirem. So if it's gamma and beta, 10 to the minus 5 joules per kilogram is a millirem. Well, if you don't know what a millirem is, it's just the same thing, right? Just another unit. What is that? Some more gobbledygook. Thank you very much. Well, this is where we'll contextualize it. 1 millirem is about what you get on average as a US citizen in a day from all natural sources combined. So what you did yesterday to incur 1 millirem is that you lived. Because you lived, you got about a millirem of radiation dose. That's the price you pay for being alive, minimum. All right. So what we're going to do is we're going to do what's called a logarithmic scale. We're going to multiply this by 2, and then 5, and then 2, and then 5. We're just going to keep multiplying to make this number get really big, really fast. We're going to come back to this 1 millirem because I picked this one intentionally because this is going to come back later. 1 millirem, that's what you get in a day. 5 millirem, is that scary? 5 times what you get in a day. Maybe, maybe not. We'll see where everybody starts to get scared. I mean, if you didn't know what 5 millirem was, that could be enough to scare you, right? I don't know. Well, let's put it in context. If I do a coast-to-coast flight, LA to New York and back, it's about 5 millirem. It's about what I get for a panoramic X-ray. They go all the way around, all my teeth all at once. From the back, you project that on the screen. It's about 5 millirem. Is that scary? Well, I'll tell you something that should scare you. I don't know, I wouldn't say it should scare you. I'll tell you something I would predict would scare you. And that's that if you found out that water you're drinking violates the EPA standard for safe drinking water, that means that if that was your only source of drinking water, you would be getting more than 5 millirem. That's the regulatory limit for drinking water. How much radioactivity you can legally have in public drinking water. If that's your only source of